Hello, Wednesday morning, November 22nd. I actually checked out this problem before going to bed last night. And while awakening this morning, I got the idea that is already in the chapter or in the section let's do it. So we have some modular function. Do we have a name for? No, it's just a modular function of weight 0. Weight 0, it says, yes. I don't know how to write that. And then we can define other functions, g of z, by choosing side classes to gamma mark. Then, so representatives or generators for the side classes. I don't know if we shall use right or left, so we'll write that later. And the number of side classes are, equal. The number of side classes equals the index of gamma mark in gamma, and since it's a modular subgroup, it doesn't say that, we assume that, then it has finite index, and let's call that n, gamma 1 to gamma n. One of them, let's say the first being the identity, of course. We have to show that these guys are what they are, what. Well, that's not necessary. We take all the symmetric polynomials. As an example, let's just take the sum. That's, I guess, sigma naught of g1 to gn. And then operated by any gamma. So we call that let's call that S naught. And this is any gamma in SL2. Over the integers. And we must put gamma I to the left here. Gamma I of gamma z. So we are using left side classes. And then this goes through all the side classes. That's what it said in the book, but I actually have to So what I need to do is to show that in each side class they have the same the same value. This is what we've got when gamma lies in gamma mark. I just realized it's only 9 o'clock, and usually I know I'm not quite awake until 10:30, so maybe that's what we are running into now. So I want to show that Gi is constant on what was the generator? That was gamma I, gamma mark. Well, we'll check that out later, whether that's it. See, we actually need to use right side classes to get that. So if we have 2 gamma marks, that's what we should show, and this is equivalent to that was a bad notation. But F O I've lost it here, totally confused. I've gone into a rabbit hole. In a way, it's very simple, but I can't get my head around it. It's time for a long break, and then I'll probably be able to do it very easily. Hello, it's 9 o'clock in the evening. It was a terrifying incident this morning, realizing that I was not able to think rationally. It has happened before, even once at an examination. I don't know if that was the one I flunked, but whatever. Usually I'm not able to see it until long afterwards, so it's a positive sign that I was able to recognize it this morning, and I've decided to leave it just so that you may learn to recognize when it happens to you that you're just experiencing a shutdown, and usually you don't have a metacognition of how you're thinking because the brain is shut down, so it's very difficult to realize. I don't know it's the first time I've been able to realize it at the time, and I don't know how to improve myself being able to do that, but I hope that was the first breakthrough. It actually seemed to be correct up until this point. Gamma lies in some side class, and we are going to use right side classes, I think. And that means that it's written as gamma mark times sum of these gammas. Let's just choose gamma 1. That shouldn't be necessary to write, though. And that means that S naught let's write it this way, of gamma z equals S naught of gamma mark gamma 1 z equals, and S naught of gamma 1 of z, and it's invariant with respect to gamma mark here, so that means it's equal to S naught of gamma 1 z and that's the sum of gi of gamma 1 z, and gi was f of gamma I of gamma 1 z. And here it actually comes in that gamma 1 just permutes the side classes it's lying in. So these are all in distinct side classes. I don't want to prove that. So that means that it's equal to the various side classes. Actually, it's easier to say than writing up formally. So I'll just write gamma dA z, where gamma I, gamma 1 equals, or lies in, gamma mark, gamma dA, where dA depends on I. So let's not prove that. That they run through all the side classes. Now we can get to the point, and that's writing up the polynomial. All the coefficients that should be first Si times x to ith. All these guys are modular functions with gamma, meaning that they lie in this field. And that means that if we add all of the functions, that's a field, then that's a splitting field for this polynomial with coefficients in the base field. And that means it's, doesn't that mean it's n-dimensional and it's a Galois extension? Well, that's the first one. It satisfies, it's the root of this polynomial of this degree, which is what we should show. Now to part B. Still November 22nd. So we have gamma naught is a normal subgroup of gamma, meaning gamma gamma n equals gamma gamma mark equals gamma mark gamma. And we have to show that G is gamma mark invariant. So we take G of gamma mark Z, which equals f of G mark alpha Z, which equals f of alpha gamma double mark, some gamma double mark in gamma mark Z equals G of gamma double mark Z, and this was in gamma mark, so it's equals, now what am I doing here? I wanted to show that it was equal to G of Z. Now the premise is that f is gamma mark invariant, and we shall show that it holds for G. But already here we can use that f is gamma mark invariant Oh, we don't even need that. I feel that I'm making a mistake here. G of gamma mark z is f of gamma mark alpha z. But we don't need this at all. Show that if gamma mark is a normal subgroup and f of z is gamma mark invariant, then so is f alpha z for any alpha. Ah, that's the mistake. All right. So it's f of alpha gamma mark z. And then we apply the normal subgroup. There we go. All right. This is the way I thought it should go. That was the first part. The field of weight zero modular functions for gamma mark is a Galois field extension. We already know that. So it's about the group action here. And we have a group action gamma mark works on the function, so f of z is mapped to f of gamma map z. And the kernel, what shall we call this map? Psi. And the kernel of psi is a subset of gamma, and it's larger than gamma mark, because for any gamma mark these two functions are equal. Oh, so we do it for any gamma in gamma, and then the kernel lies between, for any in gamma mark, this is the identity map. So we can actually, so it's all, gamma is also a normal subgroup of the kernel, of course. So we can project that means it's a subgroup. Well, that actually handles that. And of course the last thing is just the service information. I feel I'm becoming better at algebra, working on all these problems. I don't think I would have been able to do this last year, at least not so fast. A quotient, so yeah, that's what we should show. I don't mean what they mean by quotient. Oh, the kernel, of course, is a normal subgroup. So the Galois group is gamma modular the kernel. Psi. There we go. All right. I believe that solves problem 7.